Hola, chaps. Let's learn.
Hola, chaps. Mr. Turek here. I wanted to go over, this is for CP Physics, the Waves and Energy Physics Worksheet 2 that I've assigned. You should have figured it out by now. So a reminder, here's the sheet. It says do these 8 problems. And I want to give you a little bit of guidance on at least a little bit of this, right? So the first one says calculate the frequency of radiation for each of the following. And the first thing you should notice is that radiation means they all are traveling at the speed of light. And if they're traveling at the speed of light, that means 3 times 10 to the 8th meters per second in a vacuum. So the entire worksheet is dealing with radiation. So the entire worksheet all has the same speed, and that's the speed of light. So, among other things, there's the Greek prefixes. One of these is in nanometers, one in centimeters, one in kilometers. You, of course, should have memorized by now how many centimeters are in a meter, how many meters in a kilometer, how many nanometers are in a meter. Look up the Greek prefixes if you need to, but convert all of these to meters first and then plug it into the formula. So as an example, I just picked a random number and I said, suppose I have pi times 10 to the negative fourth centimeters. Well, there's 100 centimeters in a meter. So 3.14 times 10 to the negative fourth centimeters converts to 3.14 times 10 to the negative sixth meters. And there's only one equation that you have to deal with, and that is the speed of light is the product of the wavelength times the frequency. In this case, we're rearranging and solving for frequency. So 3 times 10 to the 8th meters per second divided by 3.14 times 10 to the negative 6 meters. Beep, 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 beep. I get a result of 9.55 times 10 to the 13th power cycles per second, which would be called a hertz. So this is an example of how you should do problem 1. Problem 2 says, great, now that you've done those calculations, how much energy is involved in each one of those 3 questions? Well, energy is given by Planck's formula. The energy of a single photon of light is equal to the product of Planck's constant times the frequency. Or, since the speed of light is equal to wavelength times frequency, you could substitute for frequency into Planck's equation and say energy is equal to hc over lambda. By the way, a lot of you doing the fill in the worksheet, when they asked you for the 2 formulas for energy, you didn't give me the 2 formulas for energy. You gave me one of them. Energy is Planck's constant times frequency. That's great. And then for the other one, you said, oh, the speed of light is wavelength times frequency. That's wrong. You should have said energy is also equal to Planck's constant times the speed of light divided by wavelength. Anyways, the value of Planck's constant, a very tiny number, is 6.626 times 10 to the negative 34th joule seconds. So when you plug that in, and by the way, you can either plug in the frequency that you calculated or the wavelength that they gave you in the first place. Since you have 2 versions here, you could use either one. And in my example, where I said, suppose my wavelength is 3.14 times 10 to the negative 4th centimeters, the energy for that photon would be 6.33 times 10 to the negative 20 power joules. On question number 3, they're asking you in what region of the electromagnetic spectrum would you find all these different values? There's 3 answers to that. Well, in my example, my wavelength is on the order of microns, 3 microns, since 10 to the negative 6 power is a micrometer. So you need to basically go find a chart and look it up. And you should study the chart and be prepared to talk about it. You already had a worksheet assigned where you had to figure out that the longest wavelengths were the radio waves, and those can be tens of miles in length, even hundreds, even thousands of kilometers in wavelength. And then as you get shorter, now you're going into microwave region, even shorter in the micron region, you're in the infrared area. When you're in a 0.7 microns or so, now you're starting to get to the red end of visible light, down to 0.4-ish microns, which would be 400 nanometers, a little less than that. Now you're at the violet end of the visible spectrum, Visible spectrum is Roy G. Biv, red, orange, yellow. Well, hopefully you know the rest, right? Red, orange, yellow, green, blue, indigo, violet. Those are the colors of the spectrum. The longest wavelength is red, the shortest one is violet. And once you get shorter than 385 nanometers or so, now you're in the ultraviolet. And then shorter than that, higher in energy, are X-rays. And above that are gamma rays. So find a chart and look up where on those choices each one of the three wavelengths were from your worksheet. Number 4, you guys screw up every year. It says the sun is so far from the earth. How much time does it take light to go from the sun to the earth? And so many of you say, oh, the speed of light is equal to wavelengths times frequency, but what's the frequency? They gave me the wavelength as the distance from the earth to the sun, and that's totally wrong. This question has nothing to do with C equals lambda times frequency. It's an old-fashioned distance equals rate times time question. That's all it is. There's the sun, there's the earth. You travel at the speed of light. How much time does it take to go this distance? That's all they're asking. Please don't goof it this year. All right, next one, number 5. Same idea as number 4, only this time they're saying, suppose I have the earth and I could travel around and around the earth. In 1 second, how long would it take light to travel around the earth? Or, phrasing it more correctly, how many times would it go around the earth in 1 second? So, of course, you need to take the radius of the earth. And here I have a capital C and a lowercase c, so try not to mix them up. Distance equals speed times time. In this case, the circumference is the distance that you're traveling, and the speed of light is the rate at which you're traveling. So lowercase c, capital C. Calculate away. And there's some interesting things I guess I can add in about that. So when we were in our classroom, it was possible for someone in Japan to hear the sound of my voice before you could hear the sound of my voice. And that's just because the speed of light is 1,000,000 times faster than the speed of sound in air. And if I was at the front of the classroom and you were way at the back, the time it takes the sound waves to travel from me to you could be longer than the time it takes electromagnetic waves to go from a microphone to a radio transmitter halfway around the world into a receiver and out a speaker or into earbuds for someone in Japan to hear the sound of my voice. So that's just a comment about the difference between the speed of light and the speed of sound here on Earth. Okay, number 6. This is the old echo problem, and you guys goofed it last time. So if you're standing here and you shout and the clip is there and you know how fast the speed of sound is, and I tell you how much time it takes for the sound to go and come back, and I tell you the speed of sound in air, you're supposed to calculate, so how far away is the cliff? And the error you guys had made in the past was you didn't recognize that you're going over the same ground twice. Well, this question, number 6, about light traveling from the Earth to the moon, remember that's called Earth shine, and back to Earth is just like the echo problem, except instead of going at the speed of sound in air, this time you're going to be traveling at the speed of light in a vacuum. Number 7, excited lithium ions give off light. So again, it's an electromagnetic question, and it's given to you in nanometers. You better learn your Greek prefixes, calculate the frequency, energy, and what color is this light? Well, of course, that just means it's like all the other problems you've already had on the sheet. So you use the formula to calculate the relationship between wavelength and frequency for the speed of light. You use Planck's formula to calculate how much energy there is in that photon. And you go back and look up the electromagnetic spectrum and identify, okay, what color is this light? So you're going to go zoom in on the visible part of the spectrum, knowing that red light is around 710 nanometers, that yellow light is around 550 nanometers. You look it up and then answer the question, well, what color is this light? Number 8, There is no need for me to tell you how to do this one. By now, you realize that it's up to you to think. All right, that's all I want to say for this session. Good luck.